Hello everyone, I'm Boan Tao. I'm going to introduce our work on mixed reality dataset and benchmarking of deep learning models for MEP classification. Mechanical, electrical, and plumbing systems are essential to the functionality and safety of any building. These systems include components like pipes, ducts, wiring, HVAC units, and so on. Ensuring that they are installed correctly is critical to construction quality control. However, inspecting MEP system on site is highly challenging for several reasons. First of all, limited visibility due to the walls, ceiling, and other building elements obstructing components. Second, tight spatial layout where many systems are co-located, often overlapping or crowded. Mixed reality gives a possible solution. By overlaying a design BIM model onto the physical environment, mixed reality enables real-time, on-site visualization of what should be built and compare with what has actually been installed. However, despite its potential, there are major gaps. There is currently no benchmark dataset for evaluating or developing AI models of mixed reality captured data specifically for the MEP inspection. This lack of data makes it hard to validate or compare different approaches, especially since mixed reality meshes are typically sparse and noisy compared to the laser scan. In this study, we have two main objectives. First, we aim to create a new dataset called MR-MEP dataset. This dataset is captured using mixed reality, specifically with the HoloLens tool, to reflect the kind of data available during a real-world on-site inspection. Our focus is on point segments correspond to MEP components, and in this version of datasets, we concentrate on pipes and ducts, two common and important classes in MEP inspections. Second, we conduct a benchmark study using these datasets. We're evaluating a range of state-of-the-art deep learning models for 3D point cloud classification to see whether we can deploy these models in real time on device settings like mixed reality headsets. To build a meaningful and accurate dataset, we start with a careful data acquisition process that captures both high-fidelity ground truth and real-world mixed reality conditions. Step 1. Laser scanning. We begin by conducting high-precision laser scan of real building environments containing visible MEP system. This data serves a baseline to create detailed digital representations. Step 2. As-built BIM modeling. From the laser scans, we generate as-built BIM model with 1-to-1 accuracy. They provide semantic and geometric labels for components, such as identifying what is a pipe and what is a duct. Step 3. As-built mixed reality mesh capture. Next, we scan the scene environment using HoloLens 2 headsets to capture as-built and mixed reality meshes. This data represents what a mixed reality device would see on site, capturing surface geometry in real time using a special mapping engine. Once we collect the mixed reality mesh and BIM data, the next step is to prepare the dataset for deep learning. This involves 4 key steps. First, mesh-to-point cloud conversion. HoloLens 2 generates triangle mesh representation, which are not directly usable for most deep learning models that operate on point cloud. So we first convert the mixed reality capture mesh into a structured point cloud by sampling the mesh surface. Second, component segmentation via BIM. Next, we're using the BIM model to guide the automatic segmentation. Specifically, we extract oriented bounding blocks from the BIM data for each MEP component. These oriented bounding blocks are used to crop out individual point segments from the mixed reality point cloud, each corresponding to one specific BIM-defined object. 3. Class annotation. Each segment is then labeled using the metadata from the BIM model. 4. Class balancing. Since the dataset is highly imbalanced, we apply several data augmentation techniques to help the model learn equally well across both the classes and to prevent bias toward the dominant class. For model selection, we select a diverse set of well-known and recent deep learning architecture, covering different families of 3D point cloud classification models, like traditional model PointNN, PointNN++, graph-based model DGCNN, transformer-based model, and a non-parametric model PointNN. For the validation strategy, to ensure a robust and unbiased evaluation, we used a 6-fold cross validation strategy. It ensures our results are not overfitting to specific geometric or lighting conditions during training. Figure 1 visually illustrates the trade-off between the accuracy and the computational complexity for a different method. The ideal region is the top left corner, high accuracy, low computation. That's exactly where PointNN sits. Also, it shows very low standard deviation across all folds, meaning it performs consistently in unseen scenes. In construct, some models like the point transformer and the endpoint MLP are located further to the right. They achieve the good accuracy but require significantly more computation. They also show high variability, indicating the potential overfitting or sensitivity to the specific scene. In conclusion, we introduced MR-MEP, the first real-world mixed reality dataset specifically designed for MEP component classification. We conduct a comprehensive benchmark study involving 9 deep learning models from different architecture families: traditional, graph-based, transformer-based, and non-parametric. Among all these models tested, PointNN emerged as the best overall performer. We hope that this can help future work in mixed reality-based construction, inspection, and automation. The figure illustrates example inspection application. It uses component-wise classification results and a geometric computation on a test scene from our MR-MEP dataset. The blue geometric in the background represents the mixed reality capture mesh. This is what HoloLens see on site during scanning. The color components overlaid on it represent our model predicted labels, classified from the point segments, compared with the ground truth label derived from the beam. Our next step is to move from the segment level classification to full semantic and instance segmentation. Another one, in future version of MR-MEP, we will continue at a broad range of MEP components, such as cable and cable trays, HVAC terminals, valves, switch, and features. Finally, our goal is to integrate the train model into the mixed reality system, such as the HoloLens 2, that supports live on-site classification, immediate visual feedback, and automatic quality control. Thank you. Thanks for listening.